Yeah. Okay. I hope you can all see this. Yeah. Okay. So before we get started, I'll like write my little introduction thing wrong pen. Um, Move the mic a bit closer to my mouth. Okay. Uh, so this is week 9, or quiz 9. I don't know what week it is. Um, Today is 4/3/25, and this is review session 9. Okay, so before we do anything new, I'm just gonna go over question 2 from the previous quiz because it looked like a lot of people had trouble with that. Hopefully, from me doing this, you can see what I was trying to convey last time, which is that nothing has changed. You just want to deal with these complex circuits the same way you would resistors. It's just the math is slightly harder. So, this is 8 ohms, this is 2 henries, this is 4 ohms plus minus VT, and this is 1/12 farads, and the IT equals 4 sine 2t amps. And the question says find VT using source transformations. So the first thing you notice here is that it says using source transformations. So many people did not use source transformations. If it says to do a method in the question and you don't do it, you will get points off. This time it was like 2 out of 10 points on the question were gone, just if you didn't use source transformations. So please read the question, because if you don't, you'll probably give the wrong answer or something like that. Um, so how do you do this question? Okay, well, to start, you want to convert your sine to cosine. And if you remember, sine is like cosine minus 90 degrees. So you can rewrite this as 4 sine 2t minus 90 degrees. Yep. And then if you want to convert this to a phasor, because we have to convert everything to the frequency domain, you say that I bar, hopefully you all remember the rules from last time, it's the magnitude times e to the j times the phase. So here would be negative j 90 degrees. One simpler simplification you can make is if you think about, on the unit circle of the real and imaginary, where negative 90 degrees is, right? It's pure imaginary component. So this is equal to negative 4j because it's just like straight down. Yeah. So that's like negative j4 amps or negative 4j amps. So that's this. So I'll write this as like negative j4. And then for the rest of these, hopefully you all know that the Z of a capacitor is negative J over omega C, and the Z of an inductor is J omega L. So negative J over, so for the capacitor, right, we get negative J over 2 times 1/12. So that's negative J over 1/6. So Z of C equals, this is going to be negative J6, right? Pretty straightforward. For the inductor, it's J times 2 times, uh, that is indecipherable. What did I write? Oh, that's 2 henries. Okay. J times 2 times 2, which is 4, or J4. So most people got that right. Yep. And so now once you have this, I'll like write it in blue on here. So this is 4 or J4, and this is negative J6. So now it wants you to use a source transformation to do it. So where do you use a source transformation? Okay, well, we have a current source, and that's the only source. So we're going to have to transform that. And we might as well just do it immediately. Hopefully you all remember like basic source transformation. It's like you take your current source with a resistor and you can convert it to a voltage source with the same resistor where the voltage is I times R. Yep, cool. So if we do that here, we end up with a circuit that looks like this. We got And now, so it's this capacitor that is the resistor here. So the capacitor is what's moving, and that'll end up here. And then we have the inductor and the resistor and the resistor. Yeah. So hopefully you see that's what the circuit would become when we source transform it. Yeah. So this is still the negative J6. This is the J4. This is the 8, and this is the 4. And one key thing to keep in mind is always remember what voltage you are trying to solve for. A lot of people like simplified all the resistors together and then found the voltage. That is not correct in this question because you are trying to find the voltage only across this 4 ohm capacitor or 4 ohm resistor, sorry. So if you simplify everything away and then find the voltage, then you'd be finding the voltage like here, and that's not useful. So we need to keep this resistor intact while we do our other simplifications. So now we're here. And oh, and so for the voltage here, it would be that I, so it's I bar times the impedance of the capacitor. So it's going to be negative J4 times negative J6, which will get us negative 24. Okay, hopefully I'll like write out another step. So it's negative 6 times negative 4 times I squared or J squared. So it's 24 times J squared, so negative 24. Yep. So this is now negative 24 volts here. You could also like flip the thing and write it as positive if you want. Yeah. Moving on. Okay, these two things are in parallel, so we can just combine those straight up. So Z equivalent, right, is going to be ZR ZL over ZR plus ZL. In this case, this is going to be 8 times J4 over 8 plus J4. And if you multiply, okay, I'll like combine the two on the top, so we get J32 over 8 plus 4J. And then if we want to make this nice, we multiply by the conjugate, 8 minus 4J over 8 minus 4J. And you get 8 times 32 is like, or I guess actually, to make our lives easier before we do that, we can divide everything by 4. So this would be like J8 over 2 plus J. It's a plus. And then we can multiply this by 2 minus J over 2 minus J. And that makes the numbers way easier. So now we have J8 times 2, so we have 16J. And then negative J8 times negative J is going to be plus 8. Just if that's confusing, just think about multiplying the terms. Yeah, it's right, I think. I believe. Let yeah. And then if we have A plus JB times A minus JB, what we end up getting is A squared plus B squared. This is not the difference of squares because there is a J. So yeah, I guess it is difference of squares, but the J makes it funky. So it's 2 squared plus 1 squared. So then we get 16 over 3, 16J over, oh, and over 5 plus 8 over 5, which is like 1.6 plus J 3.2. And that is your thing. So then if we redraw the circuit again, right, we have minus 24 volts here, still that capacitor, minus J6, and we have like some impedance box, 1.6 plus J 3.2, and that resistor. And we just want to find the voltage across this resistor. And we're like already there. We can just do this. This is a voltage divider, right? So we can say that VT, or it's not actually VT right now. That's kind of a bad notation there. This would be like V bar, and then we'll have to convert it back to the time domain. So V bar is going to be equal to that negative 24 volts times the voltage, the resistor that we're looking at, over the sum of all the things in the path. So minus J 1.6 plus 1.6, or minus J6 plus 1.6 plus J 3.2 plus 4, right? And this is math we can do. Let's see. I'll do it by hand just to show that you can. If you do it with a calculator, you'll get the same answer. So yeah. So 4 times 24, I'll do that with a calculator because I'm lazy. 96, so we get like negative 96 over 3.2 minus 6 is the thing. Okay, whatever. It's 5.6 minus 2.8 J, I believe. Yep. And then, okay, we have this. We need to, oh, and since, okay, so you can either like multiply by the conjugate, do all that, and like get an A plus JB form. Why is my speaker being weird? Anyway, so you can do all that, find that. Or alternatively, you can right here convert it to phasor form and then do the division. Because we do want this V to ultimately be in the A e to the J theta form. So it's easier if we convert it here. So how do we convert both of these into A e to the J theta? So negative 96, if you, I'm going to keep talking about the unit circle because it makes everything so much easier if you think about this like in the imaginary and real plane, right? So negative 96 is over here. So hopefully you can see that this angle is like 180 degrees. Yeah. Or you can just like leave it as 180 degrees. And it's both positive or negative 180 degrees. Both work. Um, I think in this answer key he uses negative, but it doesn't really matter. Yeah. The other way to look at that is just like negative 1 equals e to the negative j 180 or e to the j 180 degrees. So anyway, what you end up with here is 96 e to the negative. I'll just use negative. I don't, it really does not matter. But then for the denominator, you do it the way you're used to. So a equals 5.6 squared plus 2.8 squared. There's a dot here. Sorry if that wasn't clear. And that is 6.26. And then the theta is the inverse tangent of the imaginary part over the real part, which gets us negative 26.57 degrees. So we come back here, or we come back here, and we fill that in. So it's 6.26 e to the negative j 26.57. And if you divide, so if you remember how this works, you divide these two numbers and you subtract the bottom number or the bottom phase from the top phase. What you end up with is that V bar equals, um, which is it? Yeah, it equals 15.34 e to the, which is it? Negative, oh wait, let me find what I'm looking at. Yeah, e to the negative j 153.43 degrees, right? So that's the phasor voltage of here. We want it in time domain because the question started in time domain, so we just switch it back. But that's as simple as just like, plugging it in to like you just put the amplitude on the amplitude and the phase in the phase. So it would be 15.34 cosine. We bring back that 2t minus 153.43 degrees. And that's how you do that question from the quiz. I showed all of my work here. You don't need to show all of it. The only part that you need to show for a grade is like this. Honestly, I'm not sure why, but that's what's in the rubric. I do not have a part in that. So you need to show like this conversion, but going from like here to here, you can just plug that into your calculator. Like use the fraction function on your calculator. It'll save you work. Um, yeah, like you could probably if you use your calculator well enough, you could probably do this question in like 5 minutes. So, but as you can see, right, it's so read the question, use source transformations, and then it's like you don't want to destroy the resistor you're looking at, and just like make it as simple as possible. Here, like, okay, we have three things in series. We combine these, so we actually have three things in series, and then it's just a voltage divider. Yep. Cool. And then these three get added together on the denominator. You know what a voltage divider is. Yeah, that's the question from last week. Why is it negative 180 instead of 180? It does not matter. Uh, if you It's exactly the same thing. It's just the answer key I currently have pulled up uses a negative 180. If you were to use positive 180, right? So let me just like zoom in this thing here. So it was 96 e to the, I'll write j 180 here over 6.26 e to the negative j 26.57, right? So if we have this, right? 96, so you split this up into like 96 over 6.26 times e to the j 180 minus 26.57. And this would become, it was like 15.34 e to the j 100 206.57. But what we usually do in math is if you have like a 180-degree or greater angle, right? We know that 206.7 or 0.57 degrees minus 360 will be the same thing. So if I do that, 0.57 minus 360, we end up getting that same number we had before, which was negative 153.43. So both of them work. You get the same number, you'll just like have the angle expressed in a different way. That's why I was saying like it doesn't really matter. This is like a little aside. Okay. So that's last week's quiz. Hopefully that makes sense. Like it's just a resistor question. I think maybe you guys just hadn't done that in a bit, but you know, read the question, do what it says. Usually it's good advice. Um okay, so now uh continue to just do what you did before, but with impedance. Like you guys did some like op amps, at least on the homework. So you had some like op amps with capacitors and stuff, or like Thevenin equivalents. I'm not going to explain those, but I'll do some practice problems because it's literally exactly the same thing as it was with resistors. It's just now you have complex numbers instead of real numbers. The new topic is complex power, which is like weird, but uh you got to deal with it. I honestly have like you guys are like kind of in between what two quizzes were in previous years, so I don't know exactly what's going to be on it, but I'd recommend knowing the stuff that was on the homework. So on the homework, you guys had like a Thevenin equivalent, a op amp, some like mesh current stuff, some, and there was like one complex power question, and you learned complex power this week, so maybe that'll be on it. But I'll like go over the brief overview on complex power. Uh, Hold up. I had it pulled up on the textbook. The textbook has a good summary at the end of every chapter, if you're curious. That's what I'll be looking at because it's been a while since I did this, and I gotta look at this. But okay, so with complex power, let's say we have some complex voltage and we got some Z, right? Um, the power, the complex power we write as S, which is like both the real and imaginary component of power. And this is equal to 1/2 VI conjugate. Hopefully you all remember that I conjugate would equal like the if I is equal to A plus JB, then I conjugate, if you write as a little star, is A minus JB. Yeah. So that's what that is. So if you want to find the complex power that this resistor is dissipating, you'd find the current and then or you'd find the complex current and then you would take its conjugate and multiply it by the voltage. And that would be your power and times 1/2. If you're curious about why that is, look at the lecture slides. He explained it, I assume. Yeah. And then S is also equal to P average plus JQ, where P average is the average power and Q is the reactive power. The idea with this is that the average power in a circuit is like what actually gets dissipated as heat, whereas the complex power or the reactive power is like the energy that's shifted around between capacitors and inductors. So that energy is like kind of stored in the circuit, whereas P average is the power that's like actually dissipated to the world as heat. Okay, and then there's some other ways you can write this. So I'll like I'll write a couple different ways to write each of these. So P average is that, but it's also like uh this is just from the textbook. It's like VRMS times IRMS times the cosine of the phase of the voltage minus the phase of the current. And the way I personally would think about it is also equal to like S times the cosine of the phase of S because it's just the real component of it, and that's that. And likewise, this it's you know basically just if S is some imaginary number, this is the power average, and this is the Q. If this is S, and this is like the real, and this is the imaginary. You know, hopefully you're familiar enough with complex numbers by now to see what I mean by that. And this is like kind of oh, and like okay, there's like two other things you should know. Power factor, which they write as like PF equals P average over S over the magnitude of S. And that's also just equal to the phase or the yeah. So it's equal to yeah, it's the phase of the voltage minus the phase of the current, or you can think of that as the cosine of the phase of S. Yeah. And then for maximum power transfer, uh, if I have maximum power transfer, okay, if I have some Thevenin equivalent circuit that I've simplified and it has some ZTH and VTH, and I will have some Z load, and I know this is like what do they call it? Yeah, this is Z Thevenin, and this is this like the source, or I'll call this Z source. Sorry, I'm just like going over a bunch of things here, but so for maximum power, for maximum power transfer to this might be on something. I'm sure you'll talk about this at some point. For maximum power transfer to ZL, right? We want ZL to be equal to the conjugate of ZS, which makes sense if you think about it, because maximum power transfer will be given when there's no power, when all the power is actually dissipated as heat. So that means when there's no power like being shifted around in the capacitance or inductance of the system. So if ZS is equal to like A plus JB, or I'll just give it actual numbers, maybe that'll be nicer. So this is like 5 plus J3, right? And we want to put maximum power into here. Well, then if we make this 5 minus J3, then the equivalent impedance of this would be 5 plus J3 plus 5 minus J3, and these would cancel, and you'd just be end up with 10. And this is purely real, and we like real numbers. So cool. Um, and then you make the real parts the same. That's just like from what you learned in the first half of the semester. You can either accept this as fact or just go with it. I don't know, or look it up. And then the nice equation that's like the result of all of this is the P average. So that's not S, that's the P average max. So the maximum power you can get in a scenario like this is going to be 1/8 times VS. I'll call this VS too. Yeah. 1/8 times the magnitude of Vs squared over RL. And key point, this is RL. So this is if ZL equals RL plus what do they even call this? Oh, it's like JQ. I don't know. This is I'll call it Q. Yeah. So if it's RL plus JQ, then this is only the real part of that impedance. So your power average, I'll say like power average is always positive. Or not always positive. It's always, well, it should always be positive because you can't like dissipate negative power because then you'd be like sucking heat away from the world, and that's kind of odd. Is always real positive. All right, real and positive. Real and positive. Wow. Okay. I've talked for half an hour. I will now do practice problems. So wait, that's the homework. Okay. What is this? That's the homework. Okay, this is a quiz. Okay. So I'm not gonna do a no voltage question. You already know that. Oh, that's last week's quiz. Okay. Here we are. What do I want to do first? What will be the most useful? Hmm. Okay, I'll do this. Okay, so start Thevenin equivalent question. Oh, I spelled it wrong. Thevenin equivalent. Equivalent. Okay, so we got hmm, A, B, C, negative J3, J6, 4, 4, and 24, 0 degrees. And it says get Thevenin circuit with respect to uh, B and C. So what do we have to do? We just do the Thevenin equivalent circuit the way you've always known how to do the Thevenin equivalent circuit. Also, if you see this angle notation, hopefully is pretty clear. This is just like 24 e to the j0. That's what the angle 0 degrees means. So how do we do that? Okay, so first we want to find we have to find the Thevenin voltage and the Thevenin resistance. So I'll start with VTH. VTH, so between B and C. So the first thing you can do actually is say, okay, we don't care about A, so this thing doesn't exist. So just ignore that. So for VTH, what we're going to do is say, okay, what do we want? We want to find the voltage between B and C, or I'll do this with a laser point. We want to find the voltage between B and C, which is the voltage here. So what we really want is the voltage across this resistor. Luckily for us, these are just all in series. This is like as simple as a circuit can get. So we just need to do a voltage divider equation with this resistor. So VTH is going to be equal to, make this an equal sign, that 24 volts as the input times 4 over 4 plus J6 plus 4. This is a 4, not a 9. Sorry about that. Okay, so then this becomes 96 over J6 plus 8. I can divide things by 3 if you want. Nah, I won't. Um, I'll just flip that in a J6 plus 8, so, or not flip that. I'll turn this into A plus e to the J theta form. So A is going to be the square root of 6 squared plus 8 squared, which is that a nice number? I think it might be. 6 squared plus 8 squared, power 0.5. Yeah, that's 10. That's the, oh yeah, it's the 3, 4, 5 triangle. So we got 10, and then theta is the inverse tangent of 6 over 8, which if we plug that into the calculator, we get 36.87 degrees. So if we remember 96, if we think back to the unit circle, okay, we have 96 is purely positive, so its angle is 0. So this is just 96 e to the j 0 degree. That's theta. Oops. 0 degrees over, we got 10 e to the j 36.87 degrees. Okay, you can divide 96 by 10 in your head. It's simply 9.6. And then 0 minus 36.87 is e to the negative j 36.87. Wow. And now this is our VTH. We've done it. We have the VTH. Very cool. Now we want to find the RTH. And so for RTH, if you remember, we take our circuit and we neutralize the sources and then find the resistance with respect to, or find the equivalent resistance from like the perspective of B and C. So I will, for your sake, I will redraw this real quick. So this was J6. This is equivalent to, this will be more clear. If we have B here, we have, it's like this. And hopefully it's very clear that these are in parallel, right? So we have 4, and we have J6, and we have 4. So what we have here is you can simplify this like all at once because these two are in parallel. It'll just add. It'll be 4 plus J6. Um, is that angle sign mean e to the negative j theta or e to the angle sign here? I assume you mean that it's just positive. It's just whatever is there. So like if this was 24 angle 30 degrees, it would be equivalent to 24 e to the j 30. Yeah. That yeah, there's no trick to that. That's just notation. Anyway, if we want to convert this to some box ZTH, oh, it's not R. I should have. Okay, we're here. So ZTH is going to be just these two sections in parallel. If I call this like Z1 and this is Z2, right? ZTH is going to be equal to Z1, Z2 over Z1 plus Z2, right? And that would be, okay, we got 4 plus J6 times 4 over 4 plus J6 plus 4. I'll add parentheses to make it clear. And this will be 16 plus 24J over 4. Nope, that's 8. 8 plus J6. And now this time we're going to leave it in A plus JB form because generally you leave impedances in A plus JB form. So we're here. We multiply by the conjugate, which is 8 minus J6 over 8 minus J6. And this, I'm going to plug this into my calculator because I'm incredibly lazy. It's 16 plus 24J and then times 8 minus 6J. And we get, oh, my calculator is in the wrong mode. Let me switch that to A plus BI mode. Okay, we have 272 plus 96J. And then that's going to be over. Remember what I said earlier? It's like 8 squared plus 6 squared, which is 64 plus 36, which is 100. Wow, what a nice number. And then you can do this math. It is very simply 2.72 plus 0.96J. You can really put this J on either side. I forget which one I want to do sometimes. Yeah. Okay, so we have our ZTH, we have our RTH, or we have our VTH, and now we just have to like draw the final circuit. So we have our box thing. This is B, this is C, and here we have 9.6 e to the negative j 36.87 volts. And then here we have 2 point, nope, that's not a Z. Okay, 2.72 plus 0.96 or J ohms. And that's the question. That'd be it. So hopefully you can see it's the exact same as it was before. It's just now it's complex numbers. Moving on, I'll do an op-amp question. I think there was an op-amp question somewhere. Yeah, here's an op-amp question. And this one brings in power. How interesting. Um, Give me a second to draw it all. Op-amp. Okay. And then this is 2400 ohms, this is 200 ohms, this is negative J 500 ohms, and this is 2 volts, or like 2e to the J 0. And this is V L bar. Okay, so the question here is find the complex power of the load. So this is telling us to find S equals 1/2 V bar I bar conjugate. So this is your goal. You want to find the voltage here and then find these things. I think there's a nicer formula for this, actually, if I think about it. Because, actually, yeah, I think there is one. What is it? It's like, okay, they don't have it written here, but yeah, you can just remember the one equation and use that. So, oh, I think what it is it's like, never mind. I'll ignore it. Okay, so this is just an op-amp question. You know how to do op-amp questions. We have 0 volts here because it's connected to ground. So then VP equals VN, right? Then we also have 0 volts here. And then we just write a little note equation. So I'll say at Vn, we have 0 minus 2 over 200 minus J500, right? Because these two are in series, plus 0 minus V out over 2400 equals 0. That's our whole note equation. And then we just solve this for V out. So we got, I'll shift things around a bit. We have V out over 2400 equals negative 2 over 200 minus J500. Yep. Yeah. And then we multiply by 2400. So V out equals negative 4800 over 200 minus J500. And then we just have to simplify this. So before I do anything, I'll just tack 2 zeros off of each number. So now we just have minus 48 over 2 minus J5. And if we get that 2 in minus J5, give me a second. Yeah. Well, I guess that's a interesting way of, yeah. Okay, I guess I'll just leave this in A plus JB form for now. So I'll multiply by the conjugate here. This is kind of useful because when you're doing math like this, it can be when you have like conjugates and stuff, it can be useful to leave it in A plus JB form because you do have to like convert, you have to know what the imaginary part is and then make that the other sign. So we do this, and then this is negative 96 minus 240J over 4 plus 25, which gets us dot 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 negative 3.31 minus J 8.28. You can do that math. Yeah. Okay, so then SL, so yeah, I guess S of the load, we can call it, is equal to 1/2 V out here times I out conjugate. Because, right, this is the I. And then the way you can rewrite this, which is nice, is you know that V out bar is equal to ZL times I out bar, which means that I out bar is equal to V out times over ZL, right? And so this is equal to 1/2 V out. This is just a little derivation I'm doing here, and we'll get to a nice answer at the end here. Right? So it's the conjugate of that. And then you can take this, and then this is ultimately equal to the magnitude of V out squared. Oh, wait, let me move this down a bit. So this is like, if you want to memorize this equation, you can, but you don't need to. This could just make your life easier sometimes. So you have this squared over ZL conjugate. So you can either use this equation or this equation. Both of them are the same answer. I just showed you that they're the same thing. So if you were to use the first equation, like you just find the current by dividing this V out divided by ZL. Like it's the same thing, right? You can hopefully see that. So I'm going to use this one because we already have all the parts necessary for that. So if we want to find SL, then it is equal to 1/2, and then V out squared is going to be, right, the magnitude of a complex number is very simply, so it's going to be, I'll write it out like fully, right? It's negative 3.31 squared, 3.31 squared plus 8.28 squared. So this under the square root would be the magnitude, and then we square it. And then that divided by the conjugate of the the other thing, of the load, right? So up here it was positive. So down here it's negative because it's the conjugate. And if you plug all of this into your calculator and then press enter, then we get, come on. Give me a sec. That's annoying. Okay. The way they want it, which I guess it doesn't really specify, but this is equal to, take my word for this. If you have like minus, if you have a down, right? This is another way the unit circle can come in handy. If you have 1,000, so 1,000 minus 1,000, right? That's like down here. Uh, if this was like 1 and 1, then this would have the length square root of 2. But if it's 1,000 and 1,000, now we have 1,000 times the square root of 2, which is kind of like 1,4, 1,4-ish. And this angle will be negative 45 degrees. You can do that with math as well, but you know, I'm just going to write that this is equal to 14.21 e to the negative j45. So then if you plug this all in, you end up getting 1/2 times 79.52 over that 1414 e to the negative j45, which is ultimately equal to 0.028 e to the j45 degrees, and that is your power. And that would be your answer. So again, as a recap, what we do is we find the voltage here using like the same thing we've done before. And then once you have the voltage there, you use this equation, either of these, and you just plug in the numbers you have, evaluate it in your calculator, you get the answer. Very cool. Moving on. I still have time. Let's see. I'll do one more power question, I think. Is this? Oh, wait, there's one. Where was that one I saw? Okay. Yeah. I feel like there will be power on this quiz. That's just a gut feeling, though. I really don't know. I don't go to your lectures, so I don't really know what you've been talking about in class. But I remember on Friday he was talking about power. So surely if he was talking about power last Friday, then it'll be on the quiz this week. Otherwise, it's just like normal stuff, and hopefully, like you don't even need review for that because it's just the resistor circuits, but with complex numbers. I don't know how many times I can say that. Okay, so the question here is find the power factor associated with the current source. So if we remember, the power factor of the current source is, I will use this one here. So it's the phase of the voltage minus the phase of the current, right? So let me write that down here. Power factor equals, it's the cosine of the phase of the voltage minus the phase of the current. Here, the current is given as 2 amps, which is equal to 2 e to the j0, right? So this is actually going to be just cosine of the voltage phase. So all we need to do is find the voltage. And if we want to find the voltage, okay, we have a current source, or we have a current, and we have three things in parallel. We just need to combine all of those into one resistor. And yeah. When do you use the S equals P average plus JQ equation? If the question asks for one of those, there's not really one case in which you use any of these equations. You just use the ones that are useful to you at the time. I think you guys get a formula sheet for this. So you'll have like all the important ones there. If you want to derive any from the other ones, you know the math to do that. So there's no like exact formula for how to solve every problem. Just use the equations that seem useful and make sure you're using them correctly. So anyway, actually there's like a couple. Yeah, you could either get all these in parallel and then actually okay, wait, this is a low key smart way to do it. I'll do it that way. Um, I say it's a smart way to do it, but it's very simple. Just do a node voltage equation. So this is V1 and this is 0, right? At V1, we have uh -2 because it's 2 amps going in plus V1 over J5 plus V2 over or no plus still V1. There's only one voltage. I guess it's V1 minus 0, but I'll omit that. So V1 over negative J10 plus V1 over 20 equals 0. You can rewrite this quite succinctly as 1 over J5 minus 1 over J10 plus 1 over 20 equals 2. And if I plug that into my calculator on the left side there, or if I plug this into my calculator, right, we get, or simplify it in whatever way you want. It would be, I guess, okay, I'll actually like show a bit more work, right? So this is negative J over 5. Uh, that's a 5 plus negative or plus or minus negative J over 10 plus 1/20th equals 2, which you can then further simplify. I can just do this by hand. Crazy. It's a negative 0. Right, 1 over 5 is 0.2. So negative J 0.2. And then these minuses cancel. So plus J 0.1 plus 0.05 equals 2. V1 times, okay, now we have 0.05 minus J 0.0, or no, 0.1 equals 2. Yeah. You can multiply stuff. Yeah, if you want to get rid of the decimals, sure, I'll do that. But like basically you have this and then you just divide 2 by that, right? That's pretty straightforward. I'll do what they do here because it makes it look nicer. If you multiply everything by times 20, right, we're gonna get 1 minus J2 equals 2. Or no, equals 40, sorry. And then anyway, V1 equals 40 over 1 minus J2. For 1 minus J2, that A is going to be equal to the square root of 1 squared plus 2 squared, which is the square root of 3, right? No, I'm very silly, which is the square root of 5, which is like 2.24, right? 2.24 about 5. Yeah. Okay, 2.24, and then theta is equal to the tangent inverse of negative 2 over 1. If I plug that into my calculator, we get negative 63.43 degrees. So then here, right, we got V1 equals 40 e to the J0 over 2.24 e to the negative J63.43. You divide the real part, or you divide the coefficient, subtract the phase, and we get V1 equals 40 over 2.24, blah, blah, blah. It's 17.86 e to the J. Now it's just positive because you subtracted a negative number, right? That. Okay. And then remember, don't forget what the question asked you to find. It asked you to find this power factor, and the power factor is very simply cosine of the phase of the voltage. We know the phase of the voltage because it's right here. We just solved for it. So then power factor is very simply cosine of 63.43, which is 0.4473. Wow, look at that. We're so good at circuits. And that would be your answer. Cool. How did I go from negative j over 5? How did I get from negative okay. How did I get there? So 1 over j, that's just like okay, 1 over j5 is equal to, 1 over j times 1 over 5. And 1 over j, this is just like you think about it, right? So if j equals the square root of negative 1, right? By definition. And 1 is like 1 is like negative 1, right? So then if we divide negative 1 by j, then we get j, right? So this equals negative j. That makes sense? So this part becomes negative j, and this part stays as 1/5. So you end up with negative j over 5. Okay, how did you know what to put in the square root to calculate? So this is asking about this. How do I know what to put in the square root? Because we're finding, okay, I guess so we were here, right? And we just want to find the magnitude and phase of this complex number. And it's just like if we have minus 1 or minus j2 and we have 1, right? So that's like here. It's just the magnitude. So it's just the a squared plus b squared equals c squared, where c squared is the number we're looking for. So it's just 2 squared and 1 squared, and that's how you get that. Um, what are the difference for those two different PF formulas? So let me add another step here. Let me delete this. So they're not two different formulas. This one is the only formula. So it's cosine, but here for this specific question, we know that the phase of the current is 0 because the phase of the current is given, right? Like the current is given as 2 amps, and since it's just 2 amps, it's like 2 amps with 0 phase. And since it has 0 phase, we can plug 0 in for the phase. And then if it's 0, you can just cross it out. And so we just know that we're just looking for the phase of the voltage. Okay, I think I got everything there. I will do one more question, I suppose. Let's see. Um, yeah, I'll do this. Remember this one being kind of annoying. So okay. Okay. And it says this is 24. So this question is saying find um the average power and the reactive power for the inductor. So what we have to do is just find that. Pretty straightforward. Um, Determine, yeah, just that's the whole question. Okay, so this means effectively like we just have to find S, and then P average is equal to like S cosine the difference. You have the equations. The equations are on an equation sheet. Where did I write them? Yeah, it's like it's equal to that or that. I'm going to be using this one because it makes more sense in my brain. So, we want to find the voltage across this inductor and we want to find the current across the inductor because that'll let us find the S. So I'll like write that, right? S equals 1/2 P, no, it's a V bar I thing. Here, okay, one important thing to note. Actually, uh yeah. Basically, when the circuit is not as simple as it is here, you want to just actually use this equation. That equation is never wrong. So here, if we want to find this, right, this is like you can do a node voltage here with just one node. So V1, we have V1 minus 24 over J3 plus V1 over 2 plus V1 over negative J6 equals 0. We get V1 times 1 over J3 plus 1/2 plus 1 over negative J6 equals 24 over J3. You know, I just like took this, and this, factored out the V1, and then took this and moved it to the other side. Yeah. And then if you want to be really fast about it, you just put this in your calculator, put this in your calculator, and you just find V1. So I'll do that right now. So if I take in my calculator, I put parenthesis 24 divided by, and then another parenthesis to make sure that the 3 actually stays with the J. Okay, so we get 24 over negative 3J. Actually, okay, this is silly. I can do one more intermediate step just to show, like, yeah. So this is negative J over 3 plus 1/2 plus J over 6. And that equals 24 over 3 is 8 and 1 over J. So it's going to be negative J8. Cool. Yeah. So if we plug this all in using like the fraction button on my calculator to make everything all nice, negative J8 divided by parenthesis negative J over 3 and then plus 1 over 2 and then plus 1 over negative J over 6. We get, when we make it a decimal form, yeah, we get, I'll say dot, 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 because you should know how to do this. I can't really force you to learn how to do this. We get that V1 equals 4.8 minus J 14.4. You can get that directly to your calculator. Yeah. Well, that's like assuming you have a TI-84, which I guess is an unfair assumption for some people. My bad. But anyway, so that, however, is V1. We have found V1. This is not the final answer, right? So we have V1. We need to find the voltage for the inductor and the current through the inductor, right? So the voltage for the inductor is going to be equal to the voltage difference across it, which is going to be 24 minus V1, which is equal to 24 minus 4.8 minus J 11 or 14.4, which is equal to 19.2 plus J 14.4. Cool. And then it is easier if we now convert this to phasor because it'll make our lives easier in a little bit. Actually, you like don't really need to. Yeah, I'm gonna choose not to because we want to find like you can pick whether you want to do phasor form or not. And I'm going to pick not to. So we have this, and now we want to find the current, right? And that is going to be okay, it's going to be VL over ZL, which is going to be 19.2 plus J 14.4 over J3. If you do this math, you'll end up getting, let's see, 19.2. You can just do this like piece by piece. 19.2 over 3 is 6.4. So it's 6.4 times negative J, because remember 1 over J is negative J. And then 14.4 over 3 is 4.8. And here the J's will just cancel. So it's 14.8. And let me just check my work to make sure that I'm not making anything up right now. Yeah, so it's, no, not 14.8, sorry. This is 4.8. Okay, anyway, then we get 4.8 minus J 6.4. So then so this is I bar. So then I bar conjugate is 4.8 plus J 6.4. Crazy. I know. So then if we want to find S, I'll plug it back. I'll draw a little arrow. S equals 1/2 of 19.2 plus J 14.4 times 4.8 plus J 6.4, right? Because it's 1/2 V bar I bar conjugate. And then this, if I plug this into my calculator, let's see what I get. 19.2 plus J 14.4, and then 4.8 plus J 6.4. We get 96J, or J96. And so now you may be thinking, okay, how do I take this and then convert it into the power average and the thing? So remember, S is also equal, this is what someone asked in the chat earlier. S is equal to power average plus Q, right? The power average is the real part, the Q is the imaginary part. So here, you can also write this as 0 plus J96. So then we have that power average equals 0 and Q equals 96. And the units, I should have said the units. The units for power are watts, and the units for Q are volts, amps, reactive. That's just a thing you need to know. Because it's not really power, so they don't call it watts, but it is still volts times amps. And then they say it's reactive because it's reactive. So that would be your final answer. Cool. And yeah, I have talked for long enough. Hopefully today was useful. I will stop the recording now.